There is a quiet assumption most of us grow up with, an assumption so ordinary that we rarely notice it shaping our lives. We assume the universe exists independently of us, that stars burn whether or not we look at them, that particles move along their paths regardless of who is watching, that reality is a finished object, already written, already decided, waiting patiently for us to stumble into it. But modern science tells a far stranger story, a story in which observation is not passive, a story in which attention is not neutral, a story in which the act of noticing changes the thing being noticed. Somewhere deep inside the equations of quantum physics, reality behaves less like a machine and more like a question waiting for an answer. And the unsettling implication of that idea is this: the universe does not fully make up its mind until it is observed. For more than a century, physicists have tried to tame this idea, to soften it, to reframe it, to explain it away. Yet it refuses to disappear. Experiments confirm it again and again. At the smallest scales of existence, particles behave like probabilities until measurement forces a decision. A wave becomes a particle, a possibility becomes a fact, and in that moment, something profound occurs. The observer enters the story, not as a character watching from the sidelines, but as a participant. This is not mysticism. It is not philosophy disguised as science. It is a measured, documented feature of the physical world. Now consider the uncomfortable extension of this idea. If observation plays a role in shaping physical outcomes, then the boundary between observer and universe is thinner than we once believed. And if that boundary is thin, then moments of observation matter. Timing matters. Context matters. Awareness matters. The universe, it seems, is not simply happening to you. In subtle but measurable ways, it is responding to you. The title of this film is not a metaphor. It is a description of a transition, an idea rooted in physics, sharpened by history, and misunderstood by popular culture. To say that your observer phase is over does not mean you have gained special powers or secret knowledge. It means something more precise and more unsettling. It means that at some point observation becomes participation. And once that threshold is crossed, reality no longer behaves the same way. If you enjoy deep, slow, burn science documentaries that explore how the universe actually works beneath the headlines, subscribe to The Boring Universe. Like this video to help it reach others who value serious science, and leave a comment telling us which part of the country you are watching from. For most of human history, the universe was understood as something solid, predictable, and indifferent. Ancient civilizations imagined a cosmos governed by gods, but even those gods operated according to fixed rules. The stars traced reliable paths. The seasons returned on schedule. Eclipses, once feared, eventually became predictable. By the time classical physics emerged in the 17th century, the idea of a clockwork universe had taken firm hold. Isaac Newton's laws of motion described a world in which every object followed precise mathematical rules. Given enough information, one could, in principle, predict the future forever. In this view, observation was irrelevant. The universe did what it did whether anyone was watching or not. This assumption worked astonishingly well. It allowed humanity to build machines, calculate planetary orbits, and eventually place spacecraft on trajectories precise enough to intersect with moving targets millions of miles away. Classical physics delivered results, and with results came confidence. The universe was objective. Reality was fixed. The observer was an outsider. That confidence began to fracture at the turn of the 20th century. As physicists pushed deeper into the structure of matter, the rules they relied on started to fail. Experiments involving heat, radiation, atomic spectra, and the behavior of electrons produced results that did not fit classical predictions. Something fundamental was missing from the picture. The first cracks appeared small and technical, but they pointed toward a revolution. Max Planck's work on blackbody radiation forced him to introduce an idea he considered mathematical bookkeeping rather than a statement about reality. Energy, he proposed, came in discrete packets, quanta. This single adjustment fixed the equations, but it carried an implication that would not stay contained. If energy itself was quantized, then the smooth, continuous universe of classical physics was an approximation, not the truth. Albert Einstein pushed this idea further when he explained the photoelectric effect. Light, long understood as a wave, behaved as if it were made of particles when interacting with matter. The conclusion was unavoidable. Light was not one thing or the other. It was both, depending on how it was measured. Observation was no longer a neutral act. The outcome depended on the experimental setup, The observer had entered the equations. At first, this duality was treated as a strange but manageable feature of microscopic systems. Physicists assumed that deeper understanding would eventually restore a clear, objective picture. Instead, the situation grew more troubling. When electrons were fired one at a time through a double-slit apparatus, they produced an interference pattern consistent with wave behavior. But when detectors were placed to determine which slit an electron passed through, the interference vanished. The electron behaved like a particle. Nothing about the electron itself had changed, only the act of measurement. This result was not philosophical speculation. It was empirical, repeatable, verified in laboratories around the world. The conclusion could not be avoided. At the quantum level, physical systems do not possess definite properties independent of observation. They exist as probability distributions described by a wave function. Measurement forces that distribution to collapse into a specific outcome. The word collapse is misleading, suggesting a physical process in space and time. What actually occurs is subtler. The mathematical description of the system changes discontinuously when information is obtained. Before measurement, the system evolves smoothly according to Schrödinger's equation. After measurement, it jumps to a state consistent with the observed result. The transition is not described by the same rules that govern ordinary physical evolution. It is something else entirely. This posed an immediate problem. If the laws of physics are complete, why do they require an external act to produce definite outcomes? Where does measurement fit into the theory? And most unsettling of all, what counts as a measurement? Early interpretations tried to draw a line between the quantum and classical worlds. Microscopic systems behaved probabilistically, while macroscopic objects remained definite. Measurement occurred when a quantum system interacted with a classical apparatus. But this explanation only pushed the problem back one step. Classical apparatuses are made of quantum particles. If quantum rules apply universally, then there is no clean boundary. The universe, at its core, is quantum mechanical. The observer cannot be so easily excluded. Niels Bohr argued that the act of measurement was fundamental and irreducible. According to his view, quantum mechanics does not describe reality as it is, but reality as it is observed. Questions about what exists independent of measurement were, in his words, meaningless. Physics was about what we can say about nature, not about nature in itself. This pragmatic approach allowed physicists to calculate outcomes with remarkable accuracy, but it left a lingering sense of incompleteness. Albert Einstein was deeply uncomfortable with this conclusion. He famously rejected the idea that reality depended on observation, insisting that the moon exists whether or not someone looks at it. To Einstein, quantum mechanics was incomplete. There must be hidden variables determining outcomes beneath the probabilistic surface. Yet decades of experimental tests, culminating in violations of Bell's inequalities, showed that no local hidden variable theory could reproduce the predictions of quantum mechanics. The randomness was not a result of ignorance. It was fundamental. By the mid-20th century, the observer effect had become an accepted, if unsettling, feature of physical theory. But its meaning was carefully constrained. Physicists emphasized that observation did not require a conscious mind. Any interaction that extracted information from a system counted as a measurement. A detector, a photographic plate, an atom interacting with another atom. Consciousness was not special. The universe did not wait for human awareness to make up its mind. This clarification was important, and it remains essential today. Yet it did not eliminate the deeper implication. Information matters. The acquisition of information changes physical outcomes. Reality at its most fundamental level is not simply a collection of objects with predefined properties. It is a network of potentialities constrained by interactions. Over time, a new language emerged to describe this view. Quantum states encode information. Measurement updates that information. Entanglement links systems such that information about one immediately constrains the description of another, regardless of distance. The universe, in this picture, resembles an evolving informational structure rather than a mechanical assembly of parts. This shift has profound consequences for how we understand observation. To observe is not merely to look. It is to participate in an interaction that reshapes the informational structure of the system. When information is gained, possibilities are reduced. The future becomes more constrained. In a very real sense, observation narrows reality. At the microscopic level, this is routine. Every interaction between particles involves an exchange of information. But as systems grow larger and more complex, something remarkable happens. Quantum possibilities decohere. Interactions with the environment rapidly suppress interference effects, making the world appear classical. This process explains why macroscopic objects do not behave like quantum superpositions. It also explains why the observer effect is subtle and easily misunderstood. Decoherence does not eliminate the underlying quantum structure. It hides it. The universe still evolves according to quantum rules, but the vast web of interactions ensures that certain outcomes become overwhelmingly likely. Classical reality emerges as a stable approximation. Observation, in this context, is not about creating reality from nothing. It is about selecting outcomes from a range of possibilities that already exist within the quantum framework. This distinction is often lost outside scientific circles. Popular discussions blur the line between measurement and consciousness, between probability and intention. As a result, the observer effect is frequently misrepresented as evidence that human thoughts directly shape reality. That claim goes far beyond what physics supports. Quantum mechanics does not grant the mind special causal powers. It does not suggest that wishes collapse wave functions or that attention alone determines outcomes. And yet, dismissing the observer effect as irrelevant to human experience misses something important. While consciousness may not be required for measurement, conscious observers occupy a unique position within the universe. Humans are not isolated detectors. We are complex systems capable of modeling the world, anticipating outcomes, and acting on those anticipations. We do not merely record information, we use it. This brings us to a quieter, more subtle transition. In classical physics, the observer could be ignored without loss. In quantum physics, the observer cannot be fully removed from the description. In complex systems, the observer becomes part of the feedback loop. Information gained influences future interactions, which in turn generate new information. The system evolves in response to its own observations. Biological organisms are built around this principle. From the simplest bacteria to the human brain, life is an information processing phenomenon. Organisms survive by reducing uncertainty about their environment and acting on that reduced uncertainty. Observation in this sense is not passive. It is adaptive. It changes behavior, which changes outcomes. When a system is capable of observing itself and adjusting accordingly, a new regime emerges. The future is no longer determined solely by initial conditions and physical laws. It is shaped by internal models and feedback. This is not a violation of physics. It is a consequence of complexity. Human beings represent one of the most extreme examples of this phenomenon. We construct narratives about the world, about ourselves, about what is likely to happen next. Those narratives guide decisions. Decisions alter environments. Environments feed back into observation. Over time, patterns stabilize. Expectations become habits. Probabilities shift. None of this requires mystical explanations. It is well within the domain of science. Yet it blurs a boundary that once seemed clear. The line between observer and participant is no longer sharp. Observation feeds into causation through behavior. This is the deeper meaning behind the idea of an observer phase. Early in the development of a system, observation may have little impact. A newborn does not meaningfully shape its environment. A passive viewer scrolling through information exerts minimal influence. But as information accumulates and models form, observation becomes entangled with action. Awareness crosses a threshold. In physics, thresholds matter. Phase transitions mark qualitative changes in behavior. Water freezes, metals become superconductors, magnetic domains align. These transitions occur when underlying parameters cross critical values. Before the threshold, one set of rules applies. After it, another. There is a compelling analogy here. When an observer gains sufficient information and agency, their role in the system changes. They are no longer merely sampling outcomes. They are shaping the probability landscape through decisions informed by observation. The system responds. This is not destiny. It is not selection by a cosmic intelligence. It is a natural consequence of feedback in complex systems. Yet from the inside, it can feel personal. Awareness arrives not as a sudden revelation, but as a recognition that watching is no longer neutral. Choices matter more. Inaction becomes a choice with consequences. The title of this chapter refers to a moment when the universe noticed us back. Not because the universe has intentions, but because the structure of interaction changed. At some point, an observer becomes a variable that cannot be ignored. In physics, this is expressed mathematically. In human experience, it is felt psychologically and socially. Modern science is only beginning to explore the implications of this idea at larger scales. Fields like complexity theory, information theory, and systems neuroscience are converging on a picture of reality in which observers and environments co-evolve. Knowledge alters behavior. Behavior alters conditions. Conditions alter future knowledge. The loop tightens. This does not grant immunity from chance. Randomness remains. Uncertainty remains. But the distribution of outcomes shifts. Paths open or close based on accumulated information. In this sense, the observer phase is not about seeing. It is about updating. Once updates accumulate beyond a certain point, the system behaves differently. Quantum mechanics revealed the first crack in the classical worldview. It showed that observation is woven into the fabric of physical law. Complexity science extends that insight upward, showing how observation and action intertwine in adaptive systems. Together, they suggest a universe less like a stage and more like a process. To understand what it means for an observer phase to end, we must move carefully. We must avoid exaggeration and superstition. But we must also avoid dismissing the implications because they are uncomfortable. Science rarely flatters human intuition. When it tells us that observation matters, it means so in precise, limited, but profound ways. The transition is not announced. There is no signal, no marker in the sky. It is recognized only in retrospect, when observation begins to constrain possibility rather than merely record it. When attention changes trajectories, when information carries weight. At that point, the observer is no longer outside the system. The observer is inside the equation. For centuries, the dominant assumption about reality was not merely that it existed independently of observers, but that it was indifferent to them. The universe in this view unfolded according to immutable laws, and human awareness was an afterthought. We were spectators in a cosmic theater, seated far from the stage, watching events that would occur whether or not anyone paid attention. This assumption felt reasonable because it matched everyday experience. A mountain does not vanish when you turn away. The sun rises regardless of who notices it. Reality appears stable, continuous, and stubbornly objective. But this sense of stability is deceptive. It is an emergent property, not a fundamental one. The apparent solidity of the world arises from layers of averaging, interaction, and information loss. Beneath those layers, reality behaves very differently. To understand what it means to move beyond an observer phase, it is necessary to dismantle the illusion of passivity and examine how deeply participation is embedded in the structure of the universe. At the microscopic level, passivity simply does not exist. Every interaction alters the systems involved. When a photon strikes an electron, both change. When two particles scatter, information is exchanged. Measurement is not a special category of event imposed by scientists. It is a natural consequence of interaction. What we call observation is simply a particular type of interaction in which information about a system becomes correlated with another system. The universe is constantly observing itself. What makes human observation seem different is not that it violates physical laws, but that it introduces memory, interpretation, and delayed consequences. A rock does not remember the force that struck it. A human does. Memory allows past observations to influence future actions. Interpretation allows raw information to be converted into meaning. Together, these abilities turn observation into a driver of causation. This distinction is crucial. Physics does not suggest that consciousness creates reality out of nothing. Instead, it shows that information changes what can happen next. In simple systems, those changes are negligible. In complex systems, they accumulate. Over time, the difference between passive presence and active participation becomes impossible to ignore. Consider the idea of probability. In classical physics, probabilities reflect ignorance. If you flip a coin, the outcome appears random because you lack precise knowledge of the forces involved. In principle, if every variable were known, the result could be predicted. Probability is a placeholder for missing information. Quantum probability is fundamentally different. Even with complete knowledge of a system's wave function, only probabilities can be predicted. The future is not hidden, it is genuinely open. Measurement does not reveal a pre-existing value. It selects an outcome from a range of possibilities. This is not a limitation of technology or intellect. It is how nature operates. When probabilities are updated through observation, the statistical structure of reality changes. Some outcomes become impossible. Others become inevitable. This process is mathematically precise and experimentally confirmed. Yet its implications extend far beyond laboratory experiments. In everyday life, humans operate within probabilistic environments. Decisions are made under uncertainty. Expectations guide behavior. When someone learns new information, their internal probability model shifts. They act differently. Those actions alter the environment, affecting the probabilities faced by others. This is not quantum mechanics in the strict sense, but it is deeply analogous. Information reduces uncertainty and constrains future outcomes. The illusion of passive reality arises because these feedback loops are slow and distributed. No single observation appears to matter. But over time, patterns emerge. Entire societies reorganize around shared information. Technologies reshape behavior. Narratives alter collective expectations. Once enough observers update in similar ways, the system undergoes a qualitative change. History provides countless examples. Scientific revolutions do not merely describe the world differently, they change how the world is interacted with. The realization that germs cause disease led to sanitation, medicine, and extended lifespans. The understanding of electromagnetism produced communication networks that reshaped human coordination. In each case, observation led to participation, and participation altered reality. This pattern repeats at every scale where information is accumulated and acted upon. In ecosystems, species adapt based on environmental feedback. In economies, markets respond to expectations as much as to material conditions. In brains, neural networks rewire themselves based on experience. Reality in these domains is not static, it is responsive. The mistake is to imagine responsiveness as intentional. The universe does not care, it does not choose. It does not prefer one observer over another. Responsiveness emerges automatically from the structure of interactions. When information flows influence behavior and behavior influences future information, a loop is formed. Once formed, it cannot be undone by ignoring it. This is where the idea of an observer phase becomes meaningful. Early in the development of a system, observation has little leverage. A child does not influence global climate. A single measurement does not collapse a macroscopic object into a new state, but leverage grows with scale, coordination, and memory. As observers gain the ability to model consequences and act collectively, their influence increases. In physics, similar thresholds exist. Below a certain temperature, thermal motion overwhelms quantum coherence. Above it, new phenomena emerge. Below a critical density, matter behaves as isolated particles. Above it, collective effects dominate. Phase transitions are not gradual. They occur when accumulated conditions cross a boundary. The transition from passive observation to active participation follows the same logic. It is not a moment of awakening or a cosmic announcement. It is a structural shift. Information becomes causally significant. Feedback loops tighten. The system begins to respond differently. This shift can be unsettling because it undermines a comforting narrative. If reality is passive, then responsibility is limited. Events happen, circumstances arise, outcomes unfold. But if observation feeds into causation, then awareness carries weight. Attention matters. Ignorance is no longer neutral. To see is to enter the loop. Modern neuroscience reinforces this view. Perception is not a direct recording of the external world. It is an active process of inference. The brain constantly generates predictions about incoming sensory data and updates those predictions based on error signals. What you experience as reality is the result of this ongoing negotiation between expectation and input. This predictive model is efficient, but it has consequences. Once a model is established, it biases perception. Certain possibilities are emphasized, others are ignored. Over time, perception shapes action, and action reshapes perception. The observer does not merely witness the world. The observer constructs a usable version of it. This construction is constrained by physical reality, but it is not determined by it. Two observers in the same environment can experience fundamentally different worlds based on prior information and expectations. Their actions diverge. The environment responds accordingly. The system branches. None of this violates physical law. It is a consequence of lawful processes operating in complex arrangements. Yet it challenges the notion that reality is something one simply stumbles through unchanged. The phrase observer face is therefore misleading if taken literally. There is no stage in which humans are pure observers untouched by participation. What exists instead is a gradient of influence. Early on, influence is negligible. Later, it is substantial. The transition occurs when information begins to guide outcomes at scale. In cosmology, there is an echo of this idea. The early universe was nearly uniform, dominated by tiny fluctuations in density. Over time, gravity amplified those fluctuations, producing galaxies, stars, and planets. Small differences mattered. Once structures formed, feedback processes took over. Star formation altered chemical composition. Planets changed stellar environments. Complexity emerged from initial conditions. Observers arise only in sufficiently complex universes, but once they do, they become part of the causal structure. They do not rewrite physical laws, but they exploit them. Technology is the clearest example. By understanding physical regularities, humans redirect energy flows, alter landscapes, and create new constraints on future events. The universe responds not because it notices intention, but because intention manifests as physical action. The illusion of passivity persists because the time scales involved are long and the feedback indirect. No single decision reshapes reality overnight, but aggregated decisions do. Entire probability distributions shift. Futures that were once unlikely become common. Others disappear. This is why the language of choice and observation feels charged. It points toward a responsibility that cannot be offloaded. Once information is acquired, pretending it does not exist does not restore neutrality. The system has already changed. The wave function has already been updated, metaphorically speaking. It is important to emphasize what this does not mean. It does not mean that individuals control the universe. It does not mean that belief overrides physics. It does not mean that attention alone guarantees outcomes. Those interpretations mistake influence for dominance. The universe remains vastly larger, more complex, and more indifferent than any observer within it. What it does mean is more subtle and more demanding. It means that awareness is a form of interaction. That knowledge alters trajectories. That participation is unavoidable once certain thresholds are crossed. In a purely classical universe, ignorance could be a refuge. In a quantum and informational universe, ignorance is simply another state with consequences. To observe is to update. To update is to constrain. And once constrained, the future unfolds along a narrower set of paths. This narrowing is not inherently negative. It is what makes stability possible. It is what allows learning, adaptation, and meaning to emerge. Without it, reality would remain a blur of uncorrelated events. Structure requires constraint. Order requires selection. The unsettling realization is that observers contribute to that selection not as rulers, but as components. The universe does not ask permission. It incorporates. When people speak loosely about being chosen, the scientific interpretation is not mystical favoritism. It is positional. Certain observers occupy states where information, timing, and context align to produce disproportionate influence. Not because they are special, but because the system has evolved to that point. This is why moments of heightened awareness often feel consequential, not because destiny intervenes, but because the feedback loops have tightened. The observer is no longer skimming the surface. The observer is embedded. To say that an observer phase is over is to say that neutrality has expired. Observation now feeds directly into outcome. The universe has not changed its rules. The observer's role within those rules has changed.